In this lesson, we're going to take a look at integrals that involve the logarithm. So let's remember that the derivative with respect to x of natural log of x is 1 over x. So if that's the case, then going the other way, the antiderivative, the integral of 1 over x dx, isn't quite natural log of x. We need to plug in an absolute value. Is natural log of absolute value of x plus c. So we're going to use that to answer the following question then. What is the integral of 1 over x plus 3 dx? To do this, we need to use a u substitution. So we'll say u is x plus 3. So the derivative of u with respect to x is 1. So du equals dx. And then making the substitution, what do we get? We get the integral of 1 over x plus 3, that's 1 over u. And we've just shown that dx is the same as du. So the integral of 1 over x dx is log x plus c. So the integral of 1 over u du is log absolute u plus c, which would be log absolute x plus 3 plus c. So indeed, that's going to be our situation, but you've got to be careful with this. If we have a problem like the following one, if I am looking at the integral of 1 over 3x plus 5, we're going to let u equal 3x plus 5, of course. So then du dx, the derivative with respect to x of u, is the derivative with respect to x of 3x plus 5. So du dx is 3. So du is 3 dx. Du divided by 3 is dx. So now where am I? I'm at the integral of 1 over 3x plus 5, 1 over u. Dx is du over 3, which is really the integral of 1 over u times 1/3 times du. So that'll pull the 1/3 out in front. So I get 1/3 times the integral of 1 over u du. Which gives me 1/3 times the natural log absolute value of u plus c. And what is u? U is 3x plus 5, so my answer is going to be 1/3 times natural log absolute value 3x plus 5 plus c will be that solution. Now, there's other kinds of problems that we can do. We can also, of course, work with problems that have a definite integral endpoints. So for example, if I'm looking at the integral from 0 to pi over 2 of sine x, over 1 plus cos x dx, we're going to let u equal 1 plus cos x. We're going to take the derivative with respect to x of both sides. The derivative with respect to x of u is going to be the derivative with respect to x of 1 plus cos x. The derivative with respect to x of u is du dx. The derivative of the sum is the sum of the derivatives, d dx of 1 plus d dx of cos x. So we get du dx is 0 plus the derivative of cosine is minus sine x. So du dx is negative sine x. Du is negative sine x dx. And I like to solve for dx, so doing that, we'll say du divided by negative sine x equals dx. But then I also need to figure out what my endpoints are. All right, so you notice my first endpoint is x equals 0. My next endpoint is x equals pi over 2. So we're going to go ahead and plug in our values there and see what we get. So u is 1 plus cos x. So if x equals 0, u is 1 plus cos x. U is 1 plus cos 0. U is 1 plus 1. U is 2. And then if x is pi over 2, our upper endpoint here, u is 1 plus cos x. U is 1 plus cosine pi over 2. U is 1 cosine of pi over 2 is what? Is 0. So the bottom endpoint is 2, the upper endpoint is 1. That's a little strange. So let's see where we are with this problem. We are now at the integral. Again, originally it was x goes from 0 to pi over 2. Sine x over 1 plus cos x dx equals. When x was 0, that became u equals 2. When x was pi over 2, that became u equals 1. Sine x upstairs we'll leave alone. On the bottom, 1 plus cos x was u. And dx was du over negative sine x. So you'll notice that the sine x's divide out. So I get this equals the integral as u goes from 2 to 1, which is backwards, which bothers me a little bit. But when the sine x's divide out, the negative down there is still an issue. So I get negative 1 over u du. If I pull the negative out, I can switch the order, right? This is negative integral as u goes from 2 to 1 of 1 over u du. All I've done is I've pulled the negative 1 out. I could make a negative 1, I guess. But if I switch the endpoints, that also multiplies by negative 1. So I could take negative 1 times another negative 1 when I switch the endpoints, as u goes from 1 to 2 of 1 over u du, which of course is just 1 times the integral as u goes from 1 to 2 of 1 over u du. The integral of 1 over u is log absolute u. So I get log absolute u as u goes from 1 to 2. So log absolute 2 minus log absolute 1. Log 1 is 0, by the way, so my answer after all of that is natural log 2. Nice little question. Okay, let's take a look at another problem using logs. This time I am going to say integral of x plus 3 over x squared plus 6x plus 2. And this is a little tricky. What I'm going to say here is u is the denominator. U is going to be x squared plus 6x plus 2. Then we're going to take the derivative with respect to x of both sides. Derivative with respect to x of u is du dx. Is the derivative with respect to x of x squared plus 6x plus 2. So I get du dx is 2x plus 6. And as always, I want to solve for dx. So du is going to be 2x plus 6 dx. So du divided by 2x plus 6 equals dx. But all of the x's have to go away if I'm going to use u substitution. That's our key idea here. So what happens? What do I get? I have the integral of x plus 3 over, now x squared plus 6x plus 2 is u, and dx is du over 2x plus 6. And you need to notice that we get cancellation. So that I have the integral x plus 3 over u times du over. Factoring out the 2 here, I get 2 times x plus 3. And you'll notice then that the x plus 3's divide out. So that's really integral of 1 over u times 1 over 2 du. I can pull the 1/2 out in front. So I get 1/2 times the integral of 1 over u du, which is 1/2 natural log absolute value of u plus c, which is going to be 1/2 natural log x squared plus 6x plus 2 plus c. So that's how that works. And the only reason we were able to do it that way was the derivative of the bottom, 2x plus 6, was a multiple of the numerator that had to divide out. So that method's not going to always work, but it worked on this problem. So I looked at several examples of using a u substitution that resulted in an answer of a log. I want to this time take a look at a derivative. What is the derivative with respect to x of x times the natural log of x minus x? How are we going to do this? We're going to look at this derivative. So the derivative of the sum is the sum of the derivatives. This equals the derivative with respect to x of x log x minus the derivative with respect to x of x. Now, to do the derivative of x log x, I need to do a product rule. So we'll say u is x, v is natural log x, u prime is 1, v prime is 1 over x. So u v prime is u prime v plus u prime v. What do we get? 1 times natural log x plus uv prime times x times 1 over x, which gives me log x plus 1. So that's the derivative of x log x. So the derivative of x log x is log x plus 1 minus the derivative with respect to x of x minus 1, and my answer is just natural log x. So let's look at this, and what does this tell us? What does this tell us? It tells us that the derivative with respect to x of x log x minus x equals natural log x, and this tells us a rule then. We can go backwards to say what? We can say then that the integral of natural log x dx just is going to go backwards. What's the antiderivative of natural log x dx? Will be x log x minus x plus c. So, that's a nice thing to remember. We'll prove that in the next course. We prove this with something called integration by parts rather than going backwards. So you'll learn that in the next course, typically. But that's a nice fact to have. So you'll notice that if we can kind of memorize that for now, I guess. And then if I ask you to go ahead and take the integral of log base 2 of x, what is that? Well, I'm going to use the change of base theorem. And I'm going to say log base 2 is the same as what? Natural log x over natural log 2 dx, change of base theorem, which is the same as the integral of natural log x times 1 over natural log 2 dx. Then I pull the 1 over natural log 2 out in front. So I get 1 over natural log 2 times the integral of natural log x dx. And we showed on the previous page, remember, that the integral of natural log x is x log x minus x plus c. So I finish this up by just saying 1 over log 2 times x log x minus x plus c, which, rewriting that, simplifying it algebraically, I get x log x over log 2 minus x over log 2. I don't need to write c over log 2. C is an arbitrary constant. Log 2 is a specific constant. So if I take an arbitrary constant divided by another constant, it's just a different arbitrary constant. So that would be my answer to that one.